A particular instance of the integral test gives us this extremely useful test called the p-test, and it's to do with functions of the form 1 over x to the power p, where p is a constant. So let's think about evaluating this integral where p is some positive constant and a is also some positive constant. There's going to be a limit, of course. 1 over x to the p is x to the negative p. So now we want to think about anti-differentiating, and there's going to be two cases. There's one case where we cannot use the power rule. That's when p is equal to 1. So let's actually take care of that case over here on the side. If p is equal to 1, the integral we're evaluating is 1 over x. So here, remember, we cannot use the power rule because then we'd be dividing by 0. So instead, our antiderivative is natural log. And this limit is infinity. Natural log of a is some constant, but natural log of b goes to infinity. So if p is 1, the power of my denominator is 1, then this is a divergent integral. If p is not equal to 1, then I just get to use the power rule. I add 1 to my exponent, and then I divide. And I evaluate this from a to b. I can factor out the 1 over 1 minus p. That's just some constant. And what I'm left with is b to the 1 minus p minus a to the 1 minus p. So let's think about what we need to figure out in order to evaluate this limit. This is some constant. I am not dividing by 0 because this is the case that p is not equal to 1. This is also some constant. b is going to infinity and the power is constant. Now let's remember what some of these limits look like when I have something going to infinity raised to a constant power. If I have the limit as x goes to infinity of x, that's of course infinity. Same with the square root of x. But if I start having a negative exponent, this is 1 over x, this limit is 0. The next one is 1 over the square root of x. This limit is 0. So there's this threshold around the power. If the power is positive, my limit is infinity. If the power is negative, my limit is 0. So this looks like infinity if my power is positive, and it looks like 0 if my power is negative. This isn't going to be equal to 0 because that's when p is equal to 1. So this translates to infinity if 1 is greater than p, and 0 if 1 is less than p. That is going to give me my p-test. The case that this limit is infinity, that's a divergent integral. The case when this is 0, the limit exists, so my integral is convergent. So this tells me in general, the integral from some positive number to infinity, 1 over x to the p, where a and p are positive constants, is divergent if something and convergent if something. So it's convergent if p is greater than 1. It's divergent if p is less than 1, and the case that p was equal to 1, we did that separately. That was divergent as well. This is the p-test for integrals. Now, why do I bring that up now? Because this is also going to give us a p-test for series. Let's say I want to evaluate this series. N is the thing that's changing. The power is constant. I think about this function 1 over x to the p. It is continuous, positive, and decreasing. By the integral test, the series does what the integral does. If the integral converges, the series converges. If the integral diverges, the series diverges. So I just get to copy these criteria down here. So this is our p-test for series. And these types of series come up quite often, so it's really nice to be able to look at them and right off the bat identify, do they converge, do they diverge? If you're asked to do this, you don't have to go via the integral test. The integral test explains why this is true, but you can immediately say by the p-test converges, by the p-test diverges. Here's a p-series. My power is 2. 2 is greater than 1, so this is a convergent series. We don't know what it converges to. If I add these all up, it gets closer and closer to some finite number. We don't know what that finite number is, but we do know that a finite number exists. It's not getting infinitely large. Think about this one for a second. Converge or diverge. Where we start doesn't matter. What matters is this constant power. Our constant power in this case is 3/2. 3/2 is bigger than 1, so this is a convergent series. Third example, think about whether this one converges or diverges. My constant power in this case is 1/2. 1/2 is less than 1. So this is a divergent series. See how quick that is with the p-test? This only applies to these very particular types of series, but when it does apply, it's very quick. Here's some pictures that are actually more or less to scale of a few of these sequences. So this is the sum of 1 over n squared. So if this is 1 over 25, this is what 1 over 36 looks like, and 1 over 49, and so on. And this converges. So the terms I'm adding are getting smaller and smaller. And as I add them up, there is some ceiling, and I don't know where that ceiling is, but there's some ceiling where each term just gets me closer and closer to the ceiling, but I never actually go over the ceiling. That's what it means to be convergent. This is also convergent. My terms are maybe sized a little bit differently, but they're still heading towards 0. They're getting smaller and smaller and smaller, and the fact that it converges means there's some invisible ceiling here, and as I keep adding these terms together, the sum is getting closer and closer to that invisible ceiling, but it never goes over. On the other hand, this series diverges. Even though these terms are going to 0, when I add them all up, this stack is getting higher and higher and higher, and there's no ceiling. It just keeps going higher and higher and higher without bound. So if I add enough terms, this stack will be 1,000,000 miles high, and if I add enough terms, it'll be 1,000,000,000 miles high. This is a divergent series.